Today we're going to be exploring continuity. So here's a warm-up. Please give this one a try. The first one's very easy. All they want you to do is plug in the number 1. They want you to plug in this number into this function. So let's do that. I honestly don't know why I actually had to do this. I for some reason wanted to show off my ability to write really neatly on this program. But it's just 2.718 inches per minute. Now for the second one is asking to find approximation for what rate is for the derivative at t equals 1. Now there's no table given, so it's not like I'm going to be using t equals 2 and t equals 0 because 1 is between those two since you don't have a table. So what we will be doing is we're going to be estimating using change in t, I suppose, being 0.001. I mean, you couldn't be more accurate and use 0.0001, but I'm just going to keep it at that bad boy right there. Let's see what we get. So I just did it, and let's find out what happened. I pretty much found out what f of 1 is, and then I found out what f of 1.001 is, and I did the slope, and got my derivative to be 2.700. I didn't put the 00, but my calculator showed it was perfectly 2.7 inches per minute squared. Whenever you take the derivative, you're really adding another time on the denominator, which is why it's minutes squared. If you're wondering why, I'll try to explain it this way. The numerator were all in inches per minute. That was 2.7207 inches per minute minus 2.7180 inches per minute, which means that the numerator, if you did the subtraction, was inches per minute. The denominator was a change in time, which is minutes. So you're dividing inches per minute by minute, which would end up giving you inches per minute squared. Now approximate how far the object will go between 0 and 1 minute. In this case, you want to do the integral, because as we discussed, the area underneath the curve it's kind of like multiplying inches per minute times minute, which would get rid of the time, giving you inches. It's also what we talked about before. For velocity versus time graph, the area represented displacement. So let's do this approximation. So I decided to do the trapezoidal rule with 4 trapezoids, and I got my necessary values because I had 4. My width or height of the trapezoid is 0.225. So we needed a separation of 0.25 between all of them, and we're going to plug into this formula right here. My handwriting is horrible, so I will say it, and I hope you are listening as I'm saying it. So the trapezoidal rule formula was 1/2. Oops, that's the wrong button. Okay, it is, let's use blue. It is 1/2 times the width that I talked about. I got that from right here, times the first and the last term, so 1 and 2.718, plus, and now these values happen twice each, which is why they're inside a parenthesis that's being multiplied by 2. 1/4, which is 0.25, so this value, plus 1/2, which is f of 1/2, which is this value, and f of 3/4, which is this value. I used fractions because they're easier to put into a small parenthesis. And now all you have to do is plug into the formula. I'm going to stop right here. Oh, Mr. S, what is this limit you speak of? I am glad you asked. The limit is the y value that a function approaches as x approaches c. And here's like the written form of it. As x gets closer to c, we want to see what happens to the y value. Here's a property. If you have 2 functions within a limit, then you can pull them apart or separate them and do the individual limits and then multiply the results of those 2 limits. So in this case, we have f of x equaling 8 as x approaches 5. We also have 2x squared you can actually separate those two functions instead of keeping them the same right here, and you can do them individually, which is why we ended up getting our result. When you have limits where you add them, where you have two functions that are being added, those can be separated as well. And for instance, this one. So you have a limit, and inside the limit we have a function which we know equals 17 as x approaches 3, and we also have plus x squared. These can't be separated. The reason why we want to separate is because we know what this is. It was set to equal 17 right there, so that's why we have this value, and then simply plug in 3 into x squared, since we can, which gives us 9, and the answer is going to be 26. So, when we have a quotient, same thing applies. We can separate the quotient and have a limit on top and bottom. Over here, if you have a constant in front of a function, or the function of the constant that can be pulled out, you can do that. For instance, the limit here does not affect the 5 at all. When you plug in 2, the 5 is unaffected, so it can be pulled out. So you can first plug in the 2 into the x cubed and then multiply 5 later. Now go ahead and do a little review on limits as well. This is just going to further strengthen your ability to do limits. See you guys tomorrow.